All right, so now in this lecture, we're going to focus on how do you identify all the stereoisomers for a given compound, okay? So we got a new vocabulary word here. So again, this is a similar chart that we had. Two different types of isomers, constitutional isomers and stereoisomers. Stereoisomers are going to have same connectivity but different spatial arrangement. A subclass of stereoisomer would be enantiomers. These are two stereoisomers where they're mirror images of one another. If they're not enantiomers, they're what we call diastereomers. Okay, so this is yet another one of these vocab words we got to know, is diastereomers. So cis-trans isomers for alkenes we talked about as being stereoisomers, but are they enantiomers or are they diastereomers, right? These guys are not simply mirror images of one another. So they would be considered to be diastereomers. All right, so again, the goal here is going to be to figure out all of your stereoisomers for a given compound. So first of all, we can use this sort of rule here, which is the maximum number of stereoisomers that you're going to have is 2 to the power of n, where n is the number of chiral centers in your molecule. Okay, so this is a big, complicated, ugly molecule here, but we can calculate pretty easily how many different stereoisomers it has just by finding all the stereocenters. So a good idea to pause and see if you can do it. It's kind of a tricky one. So here we have 1, 2, and then notice where these rings connect. I have 3 bonds and a hydrogen. If it was symmetrical in such a way about that connection, then it wouldn't be, just as is always the case. But in this case, these are 3 distinct bonds. So that is going to be another stereocenter. Same down here. So 1, 2, 3, 4, 5, 6, 7. And actually, I'm just realizing that that should be there. Sorry, that was confusing. There was a methyl group there. I don't know why it got erased, but that would make 8. Okay, so that means that there are 2 to the 8th, or 256 different stereoisomers for cholesterol. It's a lot. The more stereocenters you have, more stereoisomers you're going to have. So let's look here. Again, identify your stereocenters. I have 1 here and 1 here. So that means I have 2 to the 2, or 4, 2 squared rather, or 4 stereoisomers. And so one of the challenges that I could be is I could give you a compound like this and say, draw me all your stereoisomers. Okay, so that's what we're going to sort of work on here. The first thing you're going to do, let's just focus on drawing one and then we'll talk about how you get all of them, is to just convert these lines into either wedges or dashes. Right? Just by doing so, you created, well, I guess I can just leave it like that. You've created a specific stereoisomer. You could go in and designate both of these stereocenters as either R or S. Okay? But now let's talk about an easy way to just get all of them, okay? So first of all, now let's start with something like this that has 1, 2, 3 stereocenters. So now I'm going to take 2 cubed, or it will have 8 different possible stereoisomers. And we're going to worry about drawing all those. Okay? So the first thing I'm going to do is I'm going to just draw its enantiomer, right? The mirror image. And I can do that pretty easily by changing all of my wedges to dashes. If I went in and designated, look at the difference here in my actual RNS designation, RRS, and its mirror image will be SSR, right? So that's what you're doing when you're switching wedges for dashes, is inverting that stereochemistry. But now I need to get all the other ones, right? So the easiest thing to do is to take one of your bonds, let's just take this guy, this chlorine bond, and change just that one. This would be yet another stereoisomer of this compound. And then I can draw its mirror image, right? These are both pairs of enantiomers. right? But they are not enantiomers of each other. Enantiomers only come in pairs, right? So they are both pairs of enantiomers. The relationship between this structure and this one, or these are diastereomers. Stereomers. Same thing with this and that guy. Those are diastereomers, right? They're still stereoisomers. They're just not mirror images. They're not part of that special enantiomer pair. And then you can just keep going. So now I'm going to do the same thing, except for I'm going to switch just the methyl. Right? That creates a new stereoisomer. And then I can take that and draw its enantiomer. Boom. And then lastly, take the last bond, that hydroxyl group or that alcohol group, flip just that, and then draw its mirror image as well. And so if you looked here at paying attention specifically to the RS designation, you'll see that we've covered all the different possible grounds. So we have where they're all R's or all S's, 2 R's, 2 S's, 2 S's, 2 R's, etc. All different possible combinations have been represented. These are my 2 to the 3 different stereoisomers for this particular compound. Okay, and again, in what we see circled here are all enantiomer pairs. If they are not a pair of enantiomers, then they're diastereomers to one another. Okay, now I got to talk about a special, I'm actually going to do this all in one. This is a special situation of a meso compound, which doesn't follow that 2 to the n rule. There's less stereoisomers than you would expect by calculating from 2 to the n. And let's see why that is. So actually one example here are going to be cis and trans dimethylcyclohexane. Okay. Both of these compounds have chiral centers, right? So we could go in, this is a chiral center, this is a chiral center. Likewise, this is a chiral center, and this is a chiral center, right? So we would expect them to both have an enantiomer. It turns out that one of these doesn't, right? So remember, what is the definition of an enantiomer? It means that its mirror image is not superimposable, right? It's chiral. Well, let's just take this one here and draw its mirror image. All right, so I'll get my fancy ring here, and I'm just drawing it as if it was a mirror. Well, I still have these methyl groups. So notice that its mirror image is superimposable. Okay, so this is this phenomena called a meso compound. This is an example of a meso compound. It has stereocenters. We could go in and we could designate this as either R or S. You know, we could go through that whole process. But despite having those chiral centers, it does not have an enantiomer. Its mirror image is in fact superimposable. This will only occur when you have an even number of chiral centers. Okay, so whenever you just have one chiral center, it will always have an enantiomer pair. When you have two, you got to look out for these meso compounds where their mirror image is indeed superimposable. We could do this for trans as well. I would recommend you guys doing that on your own, but you will find that its mirror image is not superimposable, right? So it does have an enantiomeric pair, but the cis one doesn't. Okay. There's an easy way to spot whether a molecule is going to be a meso compound, and that is if it has a plane of symmetry that goes through it. Okay, so for the cis 1,2 dimethylcyclohexane, it has this plane of symmetry running through it. That's why when I take its mirror image, it's identical, right? So if you can spot whether or not a compound will be a meso compound, if you can chop it in half and have it look equivalent. These are optically inactive, which we haven't talked about in yet, but just something to keep in mind for when we get to this optical activity lecture. Okay, just things to note. Meso compounds do not have enantiomers. They are identical to their mirror image. If you draw the mirror image, all you've done is redrawn the same molecule again. That's what makes it a meso compound. You can test whether or not a meso compound, or you can spot a meso compound easily whether it has a plane of symmetry associated with it. Okay, but really the real test is whether or not its mirror image is superimposable. So there are examples. Well, so here's just another example of a compound that has a plane of symmetry associated with it. So it's a meso compound. And because of that, because you have this meso compound, it means that it doesn't follow that 2 to the n formula. There's fewer than that stereoisomers. So the 2 to the n is a maximum number. Then you got to be on the lookout for meso compounds. Again, plane of symmetry is the easiest way to spot. There are weird molecules, super rare, but nonetheless, that have some sort of like rotational symmetry associated with them, but they don't have the plane of symmetry. So the real test is to draw its mirror image and see if that mirror image is superimposable. Again, you're only going to have the situation where you can't find that plane of symmetry when you have this like kind of rotational symmetry going on here. So this molecule is a bizarre one that doesn't have a plane of symmetry, but it is still a meso compound, meaning that it is achiral. So this is another sort of vocab word. Remember, what was chiral? Chiral meant that its mirror image was not superimposable. So achiral means that its mirror image is superimposable, right? Which is what a meso compound is. Meso compound specifically is a compound where its mirror image is superimposable, but it still has stereocenters. Okay.